Welcome to In 5 Minutes. The agenda of this clip is to understand how we deduce an expression of sum in terms of Cout bar. This is going to be very important because we are going to realize the transistor level diagram where my sum is in terms of Cout bar, and the reason we do this is because as we saw in ripple carry adder that the delay from C in to Cout is very critical, and sum is not that critical because the next stage gets the Cout of the previous stage, and hence we want our Cout to come first and then our sum, because Cout goes to the next stage and Cout has to come out faster, and that's the reason we try to find out an expression of sum in terms of Cout bar. Cout bar and Cout means the same. The reason why I'm doing Cout bar, I'll talk about it a bit later in the further clips. Right now for you it's the C output, remember that. Okay, let's get started. Here when you want sum in terms of Cout bar, you need to understand that now your inputs are nothing but going to be A, B, your C input or C in, and Cout bar, and your output is going to be nothing but your sum. Here I have drawn the simplified truth table. In the previous clips we have seen how to find the generate, propagate and kill signals. For this analysis, this might not be very critical, but I have just mentioned for your reference. When we have 4 inputs, A, B, C in and Cout bar, will get 16 cases, and for those 16 cases I have written the corresponding value of sum. Let's see a few cases. So when my A is 0, when my B is 0, my C in is 0 and my Cout bar is 1, my sum is equal to 0. Let's see if I can find this out from the truth table. Yes, A 0, B 0, C in 0, Cout bar 1, my sum is equal to 0. Let's take one more case, any random case, or let's go in the order only so it's easy for you to follow. When A is 0, B is 0, C in is 1 and Cout bar is 1, my sum is equal to 1. Let's see, A is 0, B is 0, C in is 1, Cout bar is 1, my sum is equal to 1. Correct. So if you see properly, here you would have 8 such cases, A, B, C and corresponding Cout bar. This Cout bar I have got by nothing but inverting the value of Cout. So you can see the further cases, and all the cases which are underlined in the new truth table are the ones which are mapped from this truth table. However, there might be certain cases which might be missing. Let's take an example. So A is 0, B is 0, C in is 0. Where is the case where Cout bar is 0? There is no such case. So for that, if you see A is 0, B is 0, C in is 0, Cout bar is 0, because there is no such case, the sum is don't care. It does not matter to you, isn't it? Similarly, we can see one more. When A is 0, B is 0, C in is 1, again there is no case where Cout bar is equal to 0. So here it is 0, 0, 1. There's no such case where Cout bar is equal to 0. So again that becomes a don't care. So some cases, or approximately half of the cases, you will find out from this truth table on your left, and the remaining half would be don't care. So you can make a corresponding truth table like this. Once you get this, okay, for people who are trying to understand, this is the basic digital circuit which we have done in the lower classes. Basically we want to get this expression. If you can remember it, fantastic. You don't need to do this derivation. If you cannot, this is how you come to the same conclusion. So it's basic simple K-maps which will not take you a couple of minutes to understand. So once I get this truth table, I have drawn a Carnot map with 4 inputs, which A, B being 2 and C and Cout bar being the other 2. We know how to draw a K-map, so I've just mentioned everything, and here I've just corresponding to each case. Suppose when A is 0, B is 0, Cout is 0 and Cout is 0 and C in is 0, I have a don't care case. I have just filled that respective values, and now I find the min terms, and it's very straightforward. The first one is nothing but, if you look properly, it's nothing but this one, the one I am encircling with green, which says that it's nothing but correct Cout bar, because all 4 of them have this in common. Correct. The next one is going to be this square which I'm drawing with a striped tinge of pink. Okay, if you look at it properly, it is nothing but having B Cout bar as a common. Similarly, You can do it for this two terms also, don't care, and 1, which is nothing but A and B along with C, because A and B will be taken from here and C is taken common from here. So this is A, B and C. Similarly, we can find this as A C out bar. So sum is nothing but A C out bar, this is the case which I have taken here, plus B C out bar which I have taken here, plus C C out bar which I have taken here, plus A B C which I have taken here. So if you take C out bar common, it's nothing but A plus B plus C into C out bar plus ABC. In summary, what we see in this clip was very straightforward, that my inputs would be A, B, C in and C out bar, and I want a corresponding expression, or I want a corresponding value of my sum at that point of time. For that, I simplified my truth table with 4 inputs A, B, C in and C out bar, and saw the cases from the full adder truth table, and the cases which were missing are nothing but don't care. I substituted all these values in my K-map and I got the corresponding value of sum in terms of C out bar, which is nothing but sum equal to A plus B plus C, the whole bracket, into C out bar plus ABC. In the next clip, we are going to see the transistor level implementation of this expression. Hope you have followed. Stay tuned and take care.